Why does data travel differently across the internet? Imagine your data is traveling on a digital highway with two very different lanes. The express lane is for User Datagram Protocol, or UDP, while the freight lane is for Transmission Control Protocol, or TCP. See how the blue video packet zips across the express lane in an instant, while the orange file packet takes its time, carefully moving along the freight lane. Why the difference? Think of UDP like a poet writing verses, focusing on speed and flow, where missing a word here or there simply does not matter. In contrast, TCP is like an engineer drafting a manual, where every single line must be precise and in perfect order. To understand this trade-off, look at the efficiency formula, which is throughput divided by latency. Throughput is the total amount of data moving through the system, while latency is the delay or time it takes for data to reach you. When you prioritize speed, you get a higher throughput with less latency. The express lane is built for speed, represented by this stopwatch, while the freight lane is built for reliability, shown by this checkmark, ensuring no data goes missing. It is a fundamental truth of networking that one size does not fit all. Why does your video chat lag sometimes? To understand, let us look at how data travels between Alice and Bob. When Alice sends a packet, or a small chunk of data, she uses a method called TCP. Think of this like sending a letter with a signed receipt. Alice waits for a green acknowledgement, or ACK, from Bob to confirm the data arrived safely. Because every single piece must be accounted for, this ensures total accuracy. So TCP is essentially a handshake followed by an acknowledgement. But what if you need speed more than perfection? In another scenario, Alice sends a swarm of data using UDP, which is a fire and forget approach. Alice just keeps sending packets rapidly without waiting for any confirmation. If one packet gets lost in transit, it simply vanishes, but the stream continues forward uninterrupted. In this mode, raw speed is prioritized over data integrity. For tasks like loading web pages, you want the reliability of TCP to ensure nothing is missing. For live streaming, however, you prefer the speed of UDP to keep the video real time. Ultimately, you have to choose your trade-off. How does your data travel safely across the internet without everything breaking? Imagine you want to send a digital photo to a friend. To make sure it arrives in one piece, your computer uses the OSI model, which is like an onion of security layers. As your photo passes through these layers, each one adds a header, a small packet of instructions, to the data. Think of it like adding layers of labels to a package as it goes through the mail. The total packet becomes a sum of all these headers, ensuring that every relay station along the way knows exactly what to do with it. This layered approach creates a robust system where hardware and software can communicate reliably. If something attempts to cut the connection, the protective layers keep your instructions safe and intact. This is what we call modular design. By breaking complex communication into these standardized, independent layers, we ensure that different systems can talk to each other across the globe. Ultimately, your data reaches its destination because interoperability is built on consistent, universal standardization.